Question B, bromine reacts more readily with salicylic acid than with benzene. Outline the mechanism for the bromination of salicylic acid shown in reaction 2 in the flowchart. A halogen carrier is not required for this reaction. The electrophile is Br2. So that bit there is giving you a big hint as to what's going on. Phenol compounds, like salicylic acid for example, are more susceptible to attack from weaker electrophiles. That's why phenol is more reactive than benzene, and hence how we'll be answering the question that follows this in a bit. So we don't need, if you think about a normal benzene mechanism, you need to have a very, very strong electrophile. You need a positively charged ion, like the Br+, for example. In this case, because phenol is that much more reactive than benzene, it can react with a weaker electrophile like bromine. So the electrophile here doesn't need to be a full positively charged species, just the bromine molecule, which can then be polarized by the phenol molecule, is enough. Okay, so we don't need the halogen carrier. So like your other benzene reactions, we won't need the beginning and ending reaction equations to show the formation of the electrophile. We can just use the bromine as it is. So I'm going to have my salicylic acid molecule. Looks like this. Just confirm that. We bring the original question back in. There it is. I'm just copying it over from there. Reacting with bromine, Br2. Okay, so my phenol molecule, my salicylic acid in this case, is able to polarize the bromine molecule. So I need to put my partial charges, my delta plus, delta minus, onto the bromine molecule. Okay, and that's the only difference really. The rest of this is exactly the same as the electrophilic substitution mechanism you draw for benzene. Okay, so I've got my positively charged bromine particle here, curly arrow coming out of the circle of the benzene ring onto that bromine, which will allow this bond to break. Okay, so this bit is obviously is extra to what you'd normally get with electrophilic substitution reactions, but this is allowing the bromine molecule to break up, so one can substitute on, the other one then will be a byproduct. So I'm going to get an intermediate. Now if we look again, to bring in the reaction here, the bromine molecule, the bromine particle, is substituting onto carbon 4. It's going opposite the OH. So whenever you have situations like this and you're asked to do mechanisms like this, your mechanism has to mirror the compound that's actually forming. If you put the bromine on a different carbon, then it's not correct. So my bromine is going onto carbon 4, which is the carbon directly opposite OH. So carbon 4 based on the number of the OH, carbon 3 if you think of the position from the COOH, but it's going opposite the OH group on the benzene ring. So I'm going to mirror that in my mechanism here. So my OH is there, my COOH will be there. So the substitution is taking place opposite the OH. So remember, each of these carbons has got a hydrogen attached, and it's that hydrogen then we're trying to replace with the halogen. So the second part of the intermediate is to show the fact that now that the electrons have been removed from the ring, so we have a disrupted benzene ring, so we no longer use a circle, but we use that big U shape. That's got to cover the 5 carbons that aren't involved in the reaction. So nice big U shape all the way around, open, facing the carbon where the substitution is taking place with the positive charge. And now the benzene ring will want to restabilize, so it will need to regain electrons from one of these bonds. Assuming then that obviously the bromine is going to be able to hold its position, the hydrogen will lose the electrons back. So yeah, the curly arrow is coming from the bond to the hydrogen back inside the benzene ring. That's your completed intermediate, leaving us then with our final product. Benzene ring re-established, OH, COOH. Oh, I put too many oxygens, beg your pardon, COOH. And then the bromine opposite the OH. And I'm also then left with a hydrogen ion left over. I beg your pardon, no we're not. We're left with a hydrogen ion that's been left over here, and the bromine that's been removed, that's been left over from the fission of the bond here. So it's not H+, it'll be HBr as your final product forming there. The second part to this question explain why bromine reacts more readily with salicylic acid than it does with benzene. Okay, so this is using the explanation of why phenol is more reactive than benzene. All we're doing is applying it then to salicylic acid. It's the same, it's a phenol-based molecule, benzene ring with an OH attached. So you apply the concept and the chemistry of phenol onto the molecule of salicylic acid and explain it that way. Okay, so it's the same basic explanation. Whenever you're explaining why phenol is more reactive, we're taking the oxygen of the OH group. So we can say the oxygen on the OH group has a lone pair of electrons which is delocalized into the ring. Okay, underlying key sections here. All right, the lone pair of electrons on the oxygen of the OH group is delocalized into the benzene ring. That's your first marking point there. As a result of that, the electron density increases. So we've effectively got an extra pair of electrons in this delocalized ring here. So the electron density of the whole molecule is increased. Okay. This then allows the bromine molecule to polarize. Okay. Well, the salicylic acid is able to polarize the bromine molecule. And then allows the reaction to take place. So essentially what we're saying is that the benzene ring, this is an addition to a little extra point to this, but sometimes it's worth putting this one on the answer just to clarify things. The benzene compound, in this case the salicylic acid, is more susceptible to attack from an electrophile. Okay, there's a little bonus point there, which is worth adding on just to clarify things. Okay, so we're going through that again. The oxygen atom of the OH group has a lone pair of electrons, which is delocalized into the benzene ring. This increases the electron density of the benzene ring, which allows it to polarize the bromine molecule, and therefore the reaction can take place. This makes the benzene molecule more susceptible to attack from an electrophile. Hence the reason why we can just use bromine and we don't need a Br+ ion.